Welcome to the series of computer science, and in this course of artificial intelligence, a part of uninformed search technique. And if you see at the right turn side of the diagram, and this is a diagram from the book of Russell and Norvig, where we have the start and we have the end, and there are some branches. So, how the search happens is it takes simultaneously from start as well as goal, and at each step the starting point and the goal the tree traverses until there is a midpoint. So, it would be exactly the time and space would be 1 by 2. So, the implementation, there will be two types of implementation and the two types of queues. One is the front, which is for the start, and the back, which is for the goal, and simultaneously we will have another two variables for paths, for front path and back path, and the visited nodes from the front as well as the back. So, we will see that with an example here. So, if you take the same example that I have given before. So, here we would see the start state as A, and this is a binary tree, and end state as goal. Now, the depth here is going to be d is equal to 0, d is equal to 1, and d is equal to 2. In the first iteration, this is how it goes. So, at starting point, at start expand from A, and the frontier is the Q. So, Q initially it is empty. Once we explore the node, the root node A, the children are going to be B and C, that is going to be put in a queue. If you remember the BFS queue, it would be something like B, C, the first is B, then the C is coming. If it is going, the tree is pushed similar to that of first left and then right. Now, the updated frontier, this is a queue, first is B and C, which is right here, and the visited node is A, and the path that we are specifying is, for A it is none, for B the parent is A, and for C the parent is again A. Now, from the back simultaneously, this is for the first iteration. So, whatever I colored in blue is for the from this path, from the top, from the root. Simultaneously, after this step, inside the loop, if we are writing a program inside the loop, we will start from goal, from this side. Here the queue is initially empty, similar to that of here, and exploring node this G, and the parent of it is C here. The updated frontier, because it is going to be C, this will be pushed, the backward frontier, this will be pushed as C, and the visited node in the backward side is G. The updated path here is going to be none, with respect to C it is G, and so on. So, this is the first iteration. It will again go into the second iteration like this, and in the second iteration, if you start from this, see earlier we visited A, now at the starting point is B. So, from B this will go further and get into this loop. So, it would be after B it would be D and E, then it will go to C. So, this is how it will go through from the A side. Now, from the B, from the backward side, from D, C and then A. Once it reaches A, this path will get modified, and this is the path at if you proceed with in this direction for just proceed for 3 iterations. After 3 iterations, you will notice that this updated path has A, which is available in the forward path also, and at that time the search will stop. And if you notice, this takes only the 3 iterations, whereas if you take the entire queue, it would be visiting A, B, C, D, there will be more than 3 iterations. So, if you see the performance of bidirectional search, the time complexity is exactly d by 2. Why? Because one is going to be at the start and other at the goal, and we reach somewhere in the midpoint. So, approximately it is going to be d by 2, the depth by 2, and similarly the space complexity also, it is going to be exactly half, which is d by 2. And is it complete? Yes, because again it is very similar, and what we are doing at each point in time is BFS. This is BFS and this also is BFS. So, it is actually the depth by 2, it is complete and it is also optimal. The same reason being it is a breadth first search. Now, coming to the other type of search, which is the informed search. So far what we have seen is different kind of uninformed searches that included, we started off with the breadth first search, then depth first search, depth limited, iterative deepening and bidirectional search. And all these, and along with we also did a uniform cost search, very similar to that of BFS, where uniform cost search involved some kind of an edge cost. Now, we will venture into another type of search called informed search. In informed search, there is some additional information regarding the goal is available, and how do we get that additional information? It is by means of the heuristic function, which is h of n. This plays a major role in getting the information on goal, and through this information we may be able to reach the goal faster, as well as in space also we would be able to store very less memory, very less nodes in the memory. So, here is an example. Suppose we are at home here and the office is here. There is some, again this is a distance problem, the route planning, assume that this is an example of a route planning where we have to find the quick route possible from home to office. Obviously, I have drawn here as a right angle triangle, where if you see from this point to, if you see that from this point to this point it is 12 the distance, and here it is going to be 9, assume that it is in kilometers, 12 kilometers and 9 kilometers. Suppose you are taking a path from here and here, it is going to be 12 plus 9. So, it would be 21 kilometers from home to office. Instead, if you take the distance straight here, then it is going to be 12 squared plus 9 squared, which is root of this. It is not always less than 12 plus 9. This is the using the triangular inequality, where if there is an estimate of the distance from home to office, this is the heuristic, some kind of heuristic that we use. Okay, the distance, the minimum distance or some kind of distance information that I would have is this factor, root of 12 squared plus 9 squared, and this is going to be much less than the actual distance. So, this is a heuristic method, one heuristic value of the distance from home to office. So, there are other example of heuristic that I will be giving in the next slide, but before we go into that, we will just see what is an evaluation function. An evaluation function for, again for the search technique. Okay, it consists of the g of n value and h of n value, where g of n is the actual value and h of n is the heuristic value. Suppose you take this example here, and in this example we have the same example that we have did for uniform cost search. This is S, here it is F, here it is R, P and B. The heuristic value is given here 253, 176, 193, 100 and B. Always the goal, the heuristic value of the goal, here it is going to be 0, h of B is 0. So, if I map at S it is 253, at F it is 176, at R it is 193, at P it is 100 and B it is 0. Now, the actual cost g of n value is this. g of n for S to R is 80, h of n for S. So, this heuristic value indicates the straight line distance from S to B. This is actually 250, that is the meaning that we are giving the heuristic value here. So, earlier we found out that the uniform cost search from S to B, it was actually somewhere around 278. And now, if we calculate just h of n value, using just h of n value from S to B, that would be, say, from S it is going to be 253. If you start from here, S, R, it branches out to R and F, and from R it branches out to P, and from P to B, and from F to B. And if you see, from at S it is 253, from F it is 176. This is for h of S value, and R it is 193, P it is 100, and B it is 0. Okay. And whereas the real time cost was 80 and this. So, this is the difference between the heuristics and the actual cost. So, the point we are trying to make here is, this value of heuristic is going to be the estimate from the point. See, I am right now at this point, what is the distance, it is not the actual distance, but an estimated one that I could reach to the goal. So, that is the heuristic value. Now, another example of the heuristics is the 8 tile, where if you see this example, this is an 8 tile puzzle we saw in the first class, where there are 3 by 3 matrix of numbers. The goal is the numbers should be arranged sequentially like 1, 2, 3, 4, 5, 6, 7, 8, and we have to move the numbers in horizontal or vertical directions. So, that is a task, and suppose for this 8 puzzle, the number of states is going to be 8 plus 1 9, 9 because of the blank space, and that is divided by 2, the 2 is because of the vertical action and the horizontal action of moving. So, 9 factorial by 2, which is these many states, 1,81,400 states. And if we move to the next level, if it is 8 puzzle, if it is a 15 puzzle, which is a 4 cross 4 puzzle, then it will lead to 10 trillion states, and to search in 10 trillion states in real time, it is going to be next to possible, or it would take a very long time. So, how do we search in such a kind of situation? There we will use some kind of heuristics. So, again in our book, there are 2 types of heuristics that are mentioned. One is the number of misplaced tiles, which is represented as h1. Another one is h2, which is the sum of horizontal and vertical distances, and this is otherwise called as a Manhattan distance. So, we will see the example of 2 of it. Suppose you take the first one, h1, the number of misplaced tiles. See, 1 actually it should be here in this position, 1 should be here, and this 2 should be here, 3 should be here. So, the number of misplaced tiles here entirely it is going to be 8. Thus, all the tiles here are misplaced, and 0 we are not taking it because it is a blank. Now, for h2 it is the sum of horizontal and vertical distances. Suppose if you take this, this is the goal that has to be there, and let us see, we have to make 1, 2 and 3 moves. That 3 moves is indicated as 1. Now, if you take the second number, it has to be at this position, but 2 is right here. So, the movement from this position to this position is just 1. So, this is 2. So, if you could check, we will do one more example here, which is 3. The number of horizontal and vertical distances is going to be 1, 2. So, this is 3. So, this is the third tile. So, if we count the sum of all these, it is going to be 18. So, this is another type of heuristic, which is H1, and another one is H2, which is the horizontal and vertical distances. Now, we have defined the heuristics value. What is an admissible heuristic? How do we know that whatever the heuristics that we defined is correct? So, the definition goes like this, that never overestimates the goal. So, it should not be too much. In other words, the heuristic function must always satisfy h of n should always be less than or equal to h star of n, where h star is the true cost from n to the goal. So, this is the actual cost, this is a g of n, it should be g of n, and this should always be less than or equal to the actual cost. If this is the condition, then we would say okay, one of the condition is admissible heuristics, and if it is admissible heuristic, then our any search algorithm that we employ, especially the A star, which we will be doing subsequently, this algorithm will provide the least cost or the optimal solution to it. So, having the heuristics into place, we will take this example, because with this example we are going to solve the two basic informed search algorithms called greedy as well as A star. So, this is an introduction for that algorithm. We will be using this problem statement. So, this is again a map of Romania with step cost, where the nodes these indicates the place names, and the edge indicates the distance in kilometer or miles. This value is actually the g of n value, and this actually this list, it is going to be the heuristic value. So, we would be using say these values g of n, h of n, in order to find our evaluation function f of n, and our objective is to reach from point A to point B, which is the start point and end point, in optimal way, optimal in the sense the most efficient way, and for that we will be using a greedy search and A star algorithm in the subsequent sessions. Now, as a summary, we have given the details of the performance of different uninformed search technique, where you could see the completeness with respect to BFS, uniform cost search, iterative deepening and bidirectional. For depth first search, it is not complete. The reason being, it can get stuck in loop, and if the depth is somewhere infinite, it may and the search may go only in one direction, the completeness may not be the result. The time factor BFS and uniform cost search is very similar to D, with except that C by E, if it is identical, there is no edge cost, then it is D. And depth first and depth limited, there is a time cost where M is the maximum depth and L is the limit with respect to depth limited, L is less than or equal to D, and iterative deepening is very similar to that of BFS. And bidirectional, we saw it is exactly half. The space is also very much similar, and optimality, depth first search is not optimal. Yeah. Coming to the summary of the informed search, we saw the evaluation function, which is defined in terms of actual cost and the heuristic value, and also I gave two examples of heuristics from the real world. In the before we move on to the next section, here is a question from the textbook. So, consider a state space where the start state is 1 and you have some branches 2k and 2k plus 1. First question is, draw the portion from 1 to 15. Just apply this and draw the tree, and suppose if the goal state is 11, what will be the order in which, if we traverse through BFS, depth limited with limit 3 and iterative deepening search. The third question is, how will the bidirectional search work on this problem, and what would be the branching factor in each direction. So, attempt this question, we will discuss the answer in the next class. In the next session, we would be seeing the greedy search and the A star search. Thank you.